Good evening, everyone. So, welcome to the third week for the live sessions for the course Geomorphic Processes, Landforms and Landscape. It is taken by Professor Javedin Malik from the Earth Sciences Department in IIT Kanpur, and myself, Ananya Mukherjee. I am a PhD student at Earth Sciences Department, IIT Kanpur. So, till the last class, the first week, we had a very basic understanding about what we are going to be learning in this course. What are the few important aspects that we need to understand for this course, and in the second week we understood what are the influences uh, that actually factor in or play a role in the different sort of processes that we will be learning. And we learned a bit about how the earth's motion, okay, motion as in earth's rotation and earth's revolution, how those actually govern the kind of climatic patterns and changing global climate, how they are affected by these motions. So those are important for us to understand that it's not just the human influence or just our activities which causes different kind of effects on the climatic patterns that we see. A lot of it actually depends on the naturally occurring processes and on factors that are out of our control. So this is what we had dealt with in the last two sessions. So now we will move on to one of the most important category or classification of processes that actually helps in transforming the different transforming the landscape on the surface of the earth. So, as we had seen this in the first week of live session, and it's also given in the first week of the lectures. So, we have endogenic and exogenic types of geomorphic processes. Endogenic are mostly the processes or the movements that happen below the earth's surface. Okay, so these are the causes for these movements are actually residing beneath the earth, okay, below the earth, and due to these movements we see changes happening on top of the earth's surface. So we have continental building, mountain building processes. Then we have some destructive processes also like volcanism and earthquakes. And there are two kinds of mountain building processes that we see. One is where we have compression or we have convergence of two land masses and we get mountains, or we have a kind of motion where two land masses are uh, you know uh, moving past each other, okay, moving against each other. So these are some of the things that we will see in today's class. So again, before we move on to the different kind of movements and processes that occur within the earth's surface, we again need to look at the earth's interior a little more in detail than what we had seen in the first weekly session. So, as we had, talked about even before, that Earth's interior is essentially a layered structure. Okay, so the layers are, they differ in their composition, in their physical properties. So, on the basis of the physical properties and the composition both together, we can categorize the different layers and we can find out what are the changes that we see when we go from one layer to another. So earth the Earth's interior, we can classify the layers, based on two very important, properties. One is their mechanical properties, and the other one is the chemical properties. Okay. So mechanical means what are the physical parameters of each of the layers, and they differ from each other, and that is why you can give the layer information nicely for that. And the other one chemically means the changes in the composition. Okay, so one particular layer has a different composition compared to the layer below it. So based on the mechanical properties, we can classify, or we can see that the Earth's interior is divided into lithosphere, asthenosphere, mesospheric mantle, outer core and inner core. Now what lithosphere, we had discussed a little on this also. Okay. So, the lithosphere mostly consists of the crust, the entire Earth's crust, as well as the uppermost solid mantle. So, mantle, you can understand is that for the mantle, okay, suppose this is your mantle. As we go down, the kind of physical state that it is in, it changes a little. Okay, so the top part is partly solid in nature. Then you have a little bit of partially melted mantle area. We will see where that will, which layer that will fall into. And then you have mostly a liquid mantle over here. Okay. So mantle itself can exist in like three different kinds of natural states. So the lithosphere consists of the entire solid crust, the Earth's crust, and the solid part of the mantle. Then what is asthenosphere? Asthenosphere is actually below the lithosphere. Okay, so this is the partially melted part of the mantle. Most of the we will learn later on when we are talking about plates moving on the Earth's surface. It is composed of different kind of plates. Okay, so they move in different directions, and there are different kind of movements that are associated with these plates. We will see that most of these plate movements are actually happening on the asthenosphere. Okay, so the asthenosphere actually kind of helps in these plate movements or tectonic movements. Okay, then you have the rest of the uppermost part of the solid part of the mantle, the asthenosphere, and the kind of the liquid parts that we see. Okay, all are part of the mantle itself. So, over here we can see that the mantle is actually the thickest layer of the Earth's interior. Then after the mantle you have the core. Now core itself is again divided into two layers, the outer core and the inner core. The outer core is liquid in nature, and the inner core is solid in nature. We will learn, we will see in the coming slides why this different kind of states that are there for the core itself. So this was based on the physical state that the material is in the different Earth's interior layers. Now we will move on to how it can be classified based on the composition we within the Earth's interior. So on the basis of the composition, crust, mantle, okay, and then the core. So mantle itself can be subdivided into upper mantle and the lower mantle. Okay, so even in mantle, we can see that with the increase in depth, there are some compositional variations within the mantle itself. So the upper mantle part is actually it has a slightly different composition compared to your lower mantle part. and then you have the core. Then we already know that, based on the physical state of the matter of the composition over there, so the core itself has the liquid outer core and the uh, and the solid inner core. Okay, so even compositionally there is a slight variation even in these. So hence the image that you see on your left, so mostly you can see that it's a combination of both the kinds of classifications that we discussed over here. So now all the layers we have learned that there are differences in their properties, in the way that they exist and the composition that they have. So how can you delineate these layers? Like, where do you know that this layer is ended over here? Now we have moved on to the different layer of the earth's interior. So wherever these mechanical or chemical changes are seen, okay, so they demarcate those depths as sort of a discontinuity. Okay, so it's like a boundary between two subsequent layers. So between your so it can be between two major layers also. Okay, so two major layers you can have a discontinuity, and discontinuity can also occur within one layer itself, like where we have inner core, outer core. Okay, so there are different kinds of discontinuities for that. So the first discontinuity is the Conrad discontinuity, and it actually occurs between upper and lower crust. Okay, so there is a difference in the compositional uh, uh, there is a difference in the composition of upper crust and the lower crust. Okay, so due to this distinction in the composition for both upper and lower crust, we you can demarcate discontinuity between within the crust itself. So then very important discontinuity is the Moho discontinuity or Mohorovičić discontinuity. So this actually separates the crust from the mantle, and the global average depth that we see, like it has been calculated by different methods and different researchers. It's about 35 kilometers. Okay, so this is an average seen across ocean as well as continental, okay, continental regions. So Moho discontinuity is an important one because it is the kind of the first discontinuity that divides the first two layers of the earth's interior. Then you have the Rapiti discontinuity. Now, as we had seen in the previous slide, okay, so you can have distinction within one layer also based on either your mechanical, the properties, or your chemical composition. So we saw that mantle can be divided into upper mantle and lower mantle because of the difference in the composition. Okay, so where that compositional change is happening within the mantle, there is a discontinuity present even there. So that is called the Rapiti discontinuity. Okay, then you have another important discontinuity where the discontinuity that divides two major layers. You have the Gutenberg discontinuity, which is lying between the mantle and the outer core. Okay, so again here this is based on the mechanical differences as well as the chemical compositional differences between mantle and core. Then you have Lehman discontinuity. Lehman discontinuity occurs between your inner core and the outer core. So again, this discontinuity is where your compositional as well as your mechanical change is happening within the core itself. So all these discontinuities we will see in one of these slides ahead, that all these discontinuities are actually calculated, or they were kind of studied based on the passage of different seismic waves. Okay, so wave propagation is one of the very important mechanisms that is used to understand the Earth's interior. Okay, so even now the seismic waves in places are used to understand Earth's interior. Okay, so the either layering information within the crust itself, or we try to understand the kind of the variations that we see in the like below the crust also. Okay, so earthquake, the waves that are generated due to occurrences of earthquakes is also one of the very useful tools that have been used to understand the Earth's interior structures. Okay, so we will see a little more on that later on. So, as I was saying, so what are the kind of or sources or processes, okay, so that kind of help you in understanding the interior of the earth. So, you can have direct sources and indirect sources. So, you can have direct sources as in where you can measure it by yourself, okay, either the depth to the different layers, okay, or you can study the compositional variation that we see between the two layers. So for that you need samples of the material that are present at say crust and then mantle and core. Obviously getting samples for such layers can be only possible up to certain depth only as per the technologies that are present right now. Okay, so some of the direct sources where we can get the uh, get the understanding or direct kind of validation of what we are thinking is a layering structure of the earth's interior. So you can have surface rock samples, you volcanoes, then mining drilling projects, deep ocean drilling project, and integrated ocean drilling project. Okay, so when they drill, even in mining, when the mines are created and kind of they collect samples while the drilling is going on or when the mines are being constructed. Okay, so when you get the samples you can easily identify what is the composition of the material at different depths, and using those people have tried to classify the different layers of the earth's interior. But these usually give us, most of these give us information about very shallow depths, say some deeper depth information can be found from deep ocean drilling project and other kind of drilling projects that we have. Then indirect sources are those kind of evidences or observations that we can do by employing another method. So if you can understand the temperature and pressure variations, okay, so then as I mentioned before, seismic activities or the propagation of seismic waves themselves can give you information about the different layers that are present. The waves either get reflected or they can get refracted or they can straight transmit through the layers also. So using these sources we can understand the earth's interior structure also. Meteorites, obviously some of the meteorites that have been found, okay, and studied, some of the meteorites actually have a close resemblance to the compositional structure that we have in our core itself. So making these validations, comparing and correlating the samples from such sources can also help us in understanding what are the compositional variations that can be found within the earth's interior. And gravitation and magnetic field, they both serve, like if you study the gravitational field and the magnetic field of the earth, they themselves can give you information about how the layering structure of the earth's interior can help you understand uh, can why the variations in this gravitational and magnetic field is actually happening due to any of the processes or the layering effects or the compositional variations that are there in the Earth's interior. Okay, so these are some of the ways that we can study and understand the Earth's interior. So as I was saying, so these discontinuities that we were talking about, they are actually seismic discontinuities. What do you mean by seismic discontinuities? At these discontinuities, the waves, okay, the waves that have been generated due to seismic activity, if you see in this figure, okay, if this is your focus of the earthquake, so a number of waves are actually going to be forming. Okay, so these are the different waves that are generated. The most important waves that are actually generated are P waves and S waves. Okay, so the P waves and the S waves, both of them have different kind of properties also. P waves can, you know, pass through both solid and liquid, but S waves do not generally pass through liquids. Okay, so they cannot pass through liquids. So all the you know, different kind of understanding that we had, that this layer is solid but this layer is liquid. Okay, so S waves you know, help us in understanding these variations within the Earth's interior. Okay, so based on how, what are the paths that are followed by the S and P waves and the time they take to reach from one place to another, using those information, we the seismic discontinuities were actually, you know, presented. So as I had mentioned before, Conrad is between the upper and lower crust, Moho between crust and upper mantle, Repeti is between upper and lower mantle, Gutenberg between mantle and core, and Lehman between inner core and outer core. Okay, so you can most of the very important ones, like between crust and upper mantle. Okay, so since crust is a solid, okay, and you know, some part of the P waves actually, you know, in P waves, okay, so P waves can pass through both your crust and mantle and core and your inner core also. Okay, but S waves, they have a different kind of interaction. So they will get reflected from the you can see over here, from this boundary itself between your mantle and the core. Okay, so from the Gutenberg discontinuity, okay, they will not transmit through your core. It might happen that your the wave actually is reflected from this discontinuity itself, the S waves. Okay, and then as usual, the P waves, they can transmit through your mantle, and so from one point they can be detected at the other. So over here, usually what we find are, these are, you know, seismic stations. There are a number of seismic stations that are actually put in place all across the globe. Okay, so they measure the, you know, travel time of these waves from say wherever they have been generated. So using those travel times, they can you know, and the distance that they have. Okay, so they can understand the you know, the path that was taken by them, and they can, you know, understand the depth to the actually interface from where they have either, you know, been refracted or reflected from. So these are some of the ways that you can understand the Earth's interior. Then a model was generated. Okay, so in this model, if you see that this is the plot is, you know, of velocity against depth. So as you see that as the depth in is increasing, okay, so this is your core and this is your crust. Okay, so from the crust, if you go you know, deeper towards your core, you can see that the velocity actually increases. Okay, so this is your S wave and this is your P wave. Okay, you can see that through your outer core. Okay, most of your S waves are attenuated as in they are no more passing through the outer core. We, that's why we can say that the outer core is liquid. Okay, there is a difference in the velocity between your upper mantle part and the lower mantle part. Okay, so over here also sometimes we can say, since mantle is not completely liquid, okay, so they are not it's not completely liquid, so it is easier for yeah, so it is easier uh, so we can say that the S waves can pass through the mantle itself, okay, but it will not pass through outer core. And since with the studies we have seen that S waves are not passing through the outer core, the inference was made that outer core is liquid, okay. And even if you compare your P waves, okay, so when the P waves are actually entering your outer core, okay, so there is a sharp decrease in the velocity of the P wave also. So, this again helps us in understanding the nature of the layer itself. Okay. And one of the very important things that we need to know, that most of our the major the majority of the material on the earth's surface, okay, so it actually belongs to two elements, okay, so you have silica and oxygen. These two are very important and they make up most of the minerals that we see, that actually make up the rocks, and also the the minerals or the compounds that are found in the earth's interior itself. Okay, so you can see that over here oxygen and silicon actually have the major kind of percentage, and iron you can see is it does occur a the composition, we can see the percentage composition is higher, but then the iron is also it can the minerals that it forms, okay, the compounds that it forms is actually with oxygen and silicon also. Okay, so you can have iron, iron in the form of silicates. So that is why we understand that the amount or the proportion of silicon and oxygen is actually is much higher compared to all the other elements that are present. So you can see that in this table the approximate percentage by weights are given, and over here also you can see that your oxygen and silicon are at a higher range. And Earth's crust is actually where you will find most of your silicate minerals. Okay, so silicate is it's mostly in the form of SiO. Okay, so you can have different. You can have Si2O5 also. Si2 SiO2 in itself is actually the mineral quartz. Okay, it's also called silica. Okay, so silica, and this is actually one of the most abundant found mineral on Earth's crust also. So Earth's crust in itself is the solid part, okay, but it is very thin, and the total thickness of the entire Earth's crust can range from 30 to 50. Now this Earth's crust is a combination of oceanic and continental. Okay, but when you compare oceanic crust with the continental crust, you see that the oceanic crust is actually thinner, okay, compared to your continental crust. Okay, so you can see over here that oceanic crust ranges from 5 to 30 kilometer thick in places, and the continental crust can range from 50 to 70 kilometers. Okay. So this is one difference that we see, and even this differences in the thickness, it is can it the factors that are controlling this is composition as well as the processes. Okay, so the natural endogenic processes that are there, these are responsible for the differences in the thickness of continental crust and oceanic crust. So temperature of the crust, it increases with depth. We have seen even when we see the Earth's interior. So as you go deeper, the obviously the temperature is going to increase, as well as the pressure. Okay, so both of them will increase. and it's around 200 degrees to 400 degrees Celsius near the mantle crust boundary, that is your Moho discontinuity. Okay, and mostly the lighter, you have two kinds of silicates. Okay, so the silicates that are made up of silicon as well as aluminum, we also call it CL. Okay, so these are actually lighter in nature. Okay, so they are of low density, and then you have another set of minerals that can be made up of, you know, silica and mafic minerals. Mafic minerals as in you have iron and nickel, okay, manganese, magnesium. These are mostly your mafic minerals. Okay, so but these are denser in nature. Okay, so the continents, okay, so the continents are mostly made up of your lighter minerals, that is the Cl or silica and aluminum, and your CMA, okay, we can call it CMA also, silica plus mafic minerals. These are also called heavier silicates. Okay, so both are actually silicate minerals. Okay, so these are actually silicate minerals. Okay, so these are the lighter silicate minerals, and these are the heavier silicate minerals. Okay, and these are actually mostly found in oceans. Okay, so Cl is found in continents, and Cma minerals are found in the oceanic crust. So now the crust was actually delineated on the basis of the difference in the chemical composition of crust and mantle. Now mechanically, some part of the upper mantle is actually considered a part of the lithosphere. So the lithosphere actually consists of both the crust, that is the upper crust, lower crust, both oceanic and continental crust, as well as some part of the mantle. The topmost part of the mantle is also considered to be the lithosphere. Okay, so that is why lithosphere is actually called the Earth's rigid outer layer. So the outer layer of the Earth is actually the lithosphere. Okay, it's not just the crust. Chemically speaking, we can say it's the crust, but if because the mechanical or the rheologically speaking, even some part of the mantle is solid in nature. So that is why we call it the lithosphere. Okay, so it can range from 10 to 200 kilometers. Okay, so 10 to 200, you can see that some part of the oceanic crust is there, and maybe continental crust somewhere. Wherever you have the thickest continental crust also, there will be some part of the solid mantle also associated with lithosphere. Okay, asthenosphere actually lies just below the lithosphere. Okay, so asthenosphere is not exactly right under your crust, but it is actually under the lithosphere. Asthenosphere is part of the mantle. Okay, so we can say that the lithosphere, okay, is followed by asthenosphere. So the lithosphere, since it is solid, and asthenosphere is partially melted in nature, so the lithosphere actually is said to be floating on the asthenosphere. Okay, and the asthenosphere in itself can extend between 80 to 200 kilometers. Okay, so that is why I said all the plate tectonic movements that we see, where they are either coming towards each other or moving away from each other, all these movements are happening on top of the asthenosphere, just because the lithosphere can actually float over the asthenosphere. It can move easily over the asthenosphere. Now we move to the Earth's mantle. Okay, so Earth's mantle, it extends from the Moho discontinuity up to the Gutenberg discontinuity. Okay, so this entire part is actually your mantle. So this is based on the the chemical kind of variations, the compositional variations, compositional variations, as well as the where the we observe the changes in the properties of the P and S waves also. So the lower mantle actually starts from below the asthenosphere. So the asthenosphere and part of the lithosphere actually becomes the upper mantle. Okay. and the density of the mantle is much higher than the crust. Obviously that is also the reason why the the crust is floating on top of the asthenospheric layer of the mantle. So it is denser in nature compared to crust, and it ranges from 3.3 to 5.5 grams per centimeter cube. So even between within the mantle there is difference in the density values. So you have the upper mantle that has a density from 2.9 to 3.3, and the lower mantle is denser compared to upper mantle, and you have it from 3.3 to 5.7. And then as you can see that the density changes, okay, so then the composition also, that it means that the composition is also varying. And as we had talked about before, with increase in depth, the temperature that we see, okay, as we go higher or as we go deeper, so it will change and it will increase. So the we had talked that the at Moho you can have from 200 to 400 degrees Celsius as the temperature, that is below the crust. Okay, so for mantle obviously it will start around 200 or 300, and it can go all the way up to 4000 degrees Celsius at the core mantle boundary. Okay, so the outer core is it is liquid in nature, and over there also we will see that the temperature variation is again happening. So now the core is the densest. Okay, so it is very dense, and the composition, the material, everything is much denser when you are comparing even your comparing your crust and mantle. Okay, and it is mostly composed of your nickel, uh, sorry, nickel and Fe. Okay, Fe is iron. So you can do call it the Nife layer. Uh, so the core is essentially made up of two elements. Okay, nickel and iron. So again, where does the core start? Okay, that again obviously the seismic discontinuities that we had seen before, that plays a very important role to understand what is the depth to the core itself. And again, outer core is liquid in nature. Okay, when you are comparing it to crust and mantle, so since there are no S waves passing, so the travel time will differ, and S waves will get easily reflected back from the core and mantle boundary. Okay, so based on that, it has been compiled that the core lies between 2900 to 6400 kilometers. 6400 kilometers actually the Earth's radius. So now you see that the density for the core actually goes all the way up to 13.6. So that is way denser than what we were seeing for the the crust or even the mantle. The crust, the average crustal density that we say is 2.67. Okay, so you can see that when you compare it from 2.67 for your crust, and it goes all the way up to 13.6. So there is a huge variation in the density values, and that in itself gives you the idea that compositionally also the Earth's interior has a lot of variations when you go deeper. So the most important finding that has ever been found is the outer core is liquid and your inner core is solid. Now why is the outer core a liquid, compared, then it should be, first of all, if we see that there is a lot of pressure. Okay, so the pressure also increases when you go deeper. Then how is it possible that something under that much pressure is remaining kind of liquid? But actually what scientists have found out that the outer core in itself does is the pressure that is present over there is not enough to solidify the entire, the core. So the outer core is staying liquid, and because of the liquid nature of the earth's outer core, okay, that actually generates uh, you know convection, and uh, and due to the Coriolis effect that we had discussed in the last class, these two are very important for the generation of the earth's magnetic field. Okay, so earth has a magnetic field because the outer core is liquid, which is giving rise to convection currents. Okay, and that in addition to the Coriolis effect that we see due to the earth's rotational motion. Okay, these two factors play a very important role in the generation of earth's magnetic field. If our outer core, didn't was not liquid, okay, and why even mantle, we can say, there are convection currents in mantle also, but the composition of mantle varies from the composition of outer core or the entire core in general. So you need a ferromagnetic material to generate the magnetic field. So that is found from the abundance of nickel and iron that in the outer core itself. That is why it's important for outer core to stay in the liquid form, okay, as well as the composition of the outer core plays an important role in the generation of the earth's magnetic field. Okay, now inner core is solid. Okay, so the inner core being solid, okay, it actually has the rotation of the earth's inner core actually is slightly faster than the rotation of the earth's surface. Okay, so this is a physical phenomena. Obviously you have physical laws governing this, and because of that, okay, the outer core has the magnetic field, okay, but even the magnetic field, okay, for a say material to generate the magnetic field, okay, there is certain kind of temperature range that needs to be maintained. So the inner core, okay, as we go towards the center of the earth, the temperature is too high, okay, and because the solid inner core is so hot, the magnetic field is not maintained in the inner core, okay, and when the actually the inner core is solidifying, okay, some amount of heat is actually given out to the inner core itself, and that again helps in generating the convection currents that are there in the inner core when because of the earth's rotation as well as the Coriolis effect. So everything is actually connected to each other. If you change any of the phenomena or any of the subtle layering layering characteristics, uh, it would have a very different picture than what we have right now. Okay, so this is also seen when we will be learning about how the current tectonic setup has evolved. Okay, so what we have now, the kind of global climatic patterns, the flora and fauna, they differ majorly because earth in itself has evolved. Okay, earth being totally as per the different kind of hypotheses, earth was essentially a molten it was a molten planet at the start. It started cooling, okay. Now even the cooling, if if the cooling had happened in a different kind of way, where the earth's layering structure had changed, so our entire kind of the setup that we have would not have been there. So everything right now, or the way the earth has evolved, the earth has been formed, actually shows us that a very sensitive balance is required to keep everything, all the systems in place and all the systems running in a perpetual manner. So, this is why understanding the Earth's interior and how the the layers differ from each other, why they differ from each other, and what are the different aspects of it that actually govern the different processes is important for us to understand. So, now we come to the history of the plate tectonics. So, we understood, that lithosphere in itself moves over the asthenosphere, and this was obviously confirmed as a proper theory after a lot of successful and failed theories. But the first time this kind of continental drift theory, which actually explain the formation of the different continents and how the continents are, were they together before or they were not together. So, all these questions, were slightly, answerable by the continental drift theory that was given by Alfred Wegener in 1915. But the continental drift had a lot of shortcomings. It could not, the mechanisms that it proposed for the continents to be moving away or towards each other did not have that amount of force which is actually required for the continents to move such large distances. So, that was one of the major shortcoming of the Wegener's continental drift. Then with further research and studies, uh, magnetism came into picture. So, when people started studying the magnetism of rocks, so they realized that you know the there were kind of reversals, okay, magnetic reversals that was measured from rocks from different continents, and there were some samples from different continents which showed that the magnetic the orientation was same for both the samples, but they belong to different continents. So, what that gave rise to understanding that that these continents were together, but they moved away from each other, okay, either towards each other or past each other. So, these were the kind of slowly the findings that was slowly coming out. And then again continental drift was kind of again pulled back into the discussion, and people started correlating some of the aspects of the continental drift with the magnetism and the magnetic characteristics of the rocks. Then finally, Harry H.S. actually has kind of gave the idea of sea floor spreading. Okay, so if their continent was together, okay, then there was a formation of the sea, and this formation of the sea happened because the sea floor in itself was spreading. Till this time, also the entire uh, principle of plates moving had not come. So, what they said that the continents are actually on top of the ocean and that they are moving, the sea floor is spreading in itself. Okay. And this was actually seen by the finding that if you consider a oceanic ridge, okay, or a kind of a mountain chain in the ocean. So, what they found that the youngest rocks, the in age, okay, in age of formation, are found actually near the area where the sea floor was spreading. So, that is when they kind of propose that the sea floor is actually moving away from each other, and that is why the continents have moved away from each other. So, this is this was kind of the breakthrough point for understanding plate tectonics in itself. So, as even I have mentioned here, the main difference between plate tectonics and the continental drift theory is that the before continents were thought as they were moving on the oceanic rocks, okay, but that is not the case. Later on, what they realized that the oceanic rocks and continents together are moving over the Earth's interior layer. Okay, that we know is the asthenosphere. So, these were some of the geological kind of evidences that actually supported the continental drift theory, where they found that mountain chains or fold mountains. Okay, so they continued from one continent to across another continent. Then the rock types or the rock samples and kind of fossil of the flora and fauna were two similar ones are found in continents that were separated by an ocean. So this was also one of the important observation that was made by Wegener, when he proposed the continental drift theory. And obviously the study of the past climates and study of the past life, both of these paleobiogeographic and paleoclimatology, these studies and the records that were found from these studies also gave the idea that the continents were together, and the same kind of animals lived together on one continent, and then later on they moved away from each other. And there so these were some of the kind of geological evidences that was given. Now the processes or the mechanisms that were proposed by Wegener, which were faulty at that time because they could not explain the force that was required for the continents to move away from each other. So first he proposed that the drift of the continents happened from the poles to the equator. Okay, so because of the equatorial bulge that is present, we know that at equator the radius increases, or the distance from the center of the earth increases compared to poles. So he kind of gave this as one of the processes that was there. uh, and the other mechanism that was given by him, that the tidal forces that were occurring on Earth's crust, due to the gravitational pull of the moon, was kind of one of the other mechanism that was given by him. Again, the forces, the tidal forces that are caused due to this mechanism are not enough to move continents from one place to another. So these two were the important, disadvantages of the continental drift theory that was given by Wegener. So when we are talking about the evolution of the Earth, as I had mentioned even in the first, I think, session, that the timeline of the different processes, geological processes or earth processes, okay, so the timeline of them happening and making a change anywhere, or transforming the land surface somewhere, is actually very long compared to what we humans can gauge. So till now, as we had discussed, that approximately till now the Earth's age is given as 4.54 billion years old. Okay, so over here you can see that this is the geological time scale that we as geologists and earth scientists use to date rocks, to study rocks from much prior to the human civilization, or uh, the, the start of the human life. Okay, so they actually go all the way back to 4.54. Okay, then later on the first time life came. Okay, life was found on earth was actually 545 million years ago. Okay, so you can see from 4.54 billion years to 545 million years. Okay, so that entire time there was no life, but earth was evolving. Okay, so different kind of rocks are actually suggestive of this, and there are different kind of dating techniques are used to date rocks and find, and they have found that actually rocks did they were formed as early as 4 million years ago. Okay, approximate age I am saying. So you can, so today is over here. Okay, so the Holocene period or Holocene, the epoch as we say, is actually what we consider as today, or 10,000 years before us. Okay, but you can see that the time scale, okay, so the time scale is much larger for us to understand. So these continental drift theory that we say, or plates moving against each other, towards each other, away from each other, these don't happen overnight or across just few years. It takes lots of years for them to actually move even 1 centimeter, or for 1 kilometer away from each other. Per year, maybe few centimeters they are moving from each other or moving towards each other. Okay, but centimeter is very small, when you compare the entire Earth as a whole. So, geological time scale is uh, important for us to know if you are an earth scientist or a geologist, but it mostly gives us an idea of how long some processes or some incidents or events take, okay, to occur, to slowly start forming and then reach a conclusion when we are talking about the earth as a whole. So now this is the present day scenario. Okay, so these are the different continents that we have. Okay, Asia, Australia, Africa, Europe, North America, South America, Greenland and Antarctica. Okay, so these are some of the major land masses that we see, and this is kind of the setup that we have now, and this has been the setup for quite some time. Okay, but this was not the setup that was there when we when we are talking about, say, 540 million years ago. Okay, so this was not the case at that time. So how did the current setup form? Okay, so for that, we there have been research that has been conducted to understand where the continents were placed originally. India was actually a part of Antarctica and also Australia. Okay, and then how did India separate from Antarctica, and how did Australia separate, and how Madagascar also moved away from Antarctica and Indian landmass. Okay, so these were the different research has been done to understand and answer these questions. So from all the different kind of studies that have been conducted. So if we talk about around 600 million years ago. Okay, so 600 million years ago, so that is just that is before the first onset of human life. So that's when researchers have concluded that there was a supercontinent that was called Rodinia, and it split apart. Okay, so before Rodinia actually came into picture, okay, so much before any continental breakup and assembly had happened. So the first ever continent that was kind of said continent, okay, was Pangaea, and the entire oceanic body that surrounded Pangaea, okay, so that was called the Panthalassa. Okay, so this was the start. In the start, we had only Pangaea and Panthalassa. Okay. Now later on, they themselves, Pangaea broke quite a few times. It formed different kind of uh, uh, supercontinents. Okay, so some of them are not yet totally proven. So you had Nuna somewhere. Okay, so these are like not very important right now for us to know, But you can see that suppose we are considering 600 million years ago. So this entire kind of supercontinent started splitting apart from around 500 million years ago. So 100 million years from the first split of Rodinia, you can see that two different kind of supercontinents formed. Then you have Pannotia and Laurentia was splitting. Okay, so you can see over here that the different kind of you can see South America was actually a part of Antarctica over here. Okay, Arabia and Africa were also next to each other. Okay, so you can see that how the entire picture of the continental setup was changing in within 100 million years. Okay, then more like 200 million years after, or after this kind of setup, you can see that there was an assembly of different supercontinents. Laurentia collided with Baltica, and that is when your Appalachian mountains formed. So Appalachian mountains, we were saying in the continental theory that some mountain belts, they continue from one supercontinent to another sorry, not supercontinent, from one continent to another continent. Now that actually gave us an idea that actually these two land masses or these two plates were actually close to each other at certain point when the mountains had formed. Okay, so you can see over here South America, again it's still a part of Antarctica, and then Africa also joined it, and Laurentia and Baltica also came here. Now you can see the India is present here with Antarctica and Australia. Okay, then again after 100 million years of this setup, okay, uh, the entire the dinosaurs that were there, okay, so they actually came into picture. And even that time you can see that most of the continents were again together, close to each other. And then you had the the important one, that came together. And sorry, I said the it was the wrong conclusion that I had given. It was not the first supercontinent, Pangaea and Panthalassa. Pangaea was the first ever supercontinent that actually held all of the different continents together. Okay, so together the entire kind of the all the land masses that we see even now, okay, when they all came together, that time it was called Pangaea. So that was around 200 million years ago compared to the present. So I'm sorry for the previous statement that I made. Okay, so the Pangaea, again most of the oceanic part was actually Panthalassa, but between your Indian side of the Pangaea, okay, and the Eurasian side of the Pangaea, we had another ocean, that was the Tethys Ocean. Okay, okay, so this is Indian part, and then this is the Eurasian part, and you can see the Tethys Ocean was present between the Indian and Eurasian plate. Tethys Ocean actually disappeared when you had the collision between the Indian landmass and the Eurasian landmass. Then after this setup, 100 million years after that, Pangaea started breaking apart. And then when Pangaea broke apart, the different oceans started forming. Okay, that's when you got your Pacific Ocean, your Atlantic Ocean was also forming, and Tethys Ocean was present, but slowly as India moved northwards, Tethys Ocean actually closed with the collision between India and Eurasia. Okay, and around 50 million years was when different pieces of the large Pangaean continent actually started colliding with each other and started kind of structuring themselves as per the current tectonical setup that we have, or the continental setup that we have. Okay, so this was the present day scenario, and the last kind of thing that had happened, was Australian continent actually separating from Antarctica. Okay, and then because of the polar locations of say Greenland and Antarctica, because they kind of drifted away from all the other continental land masses, that is why and their current position in the polar areas, that is why you have ice caps over there, and that in itself kind of governs all the different kind of global climatic patterns that we see. Ki- uh, Whatever position is held by the continents right now, that is also responsible for the kind of climatic scenarios that we see right now across the globe. Okay, so now as we are seeing that due to global warming, and there is increase in the sea levels due to melting of ice. Okay, so these things will again have an effect on the movement between the continents. So it's a cyclic process, and each and every factor actually influences each other in during such processes. So now how are these continents actually or these plates are actually managing that the floating on the asthenosphere as well as moving. Okay, now we see that it's the densities and the thickness of the crustal material is varying. We read about that. Okay, so some areas the thickness is changing, and some crustal material has different density compared to the different like as we said, oceanic crust has a different density compared to continental crust if you consider the average density values for these. Okay, so then how are they actually staying in that balanced kind of uh, state? So we then come to the principle of isostasy to understand this. So what is this principle? It is actually the phenomena of the tectonic plates floating on the mantle. Over here, tectonic plates is the entire kind of lithospheric column, and the mantle part is actually the asthenosphere. Okay, so it is actually the principle of buoyancy also plays a role, where there is a force that is uh, a force that is exerted by the plates that are moving, okay, on top of the mantle, and there is a resisting force. Okay, so where the resisting force is not letting the material on top sink totally down. Okay, so there for it to float, there needs to be this resistive force from the mantle itself. So how much this resistive force is actually making the difference, or how much it's giving the effect in the thicknesses that we see of the different columns, that is actually studied from isostasy. So uh, so the how what would be the kind of depth of this lithospheric column for it to float on the mantle. Okay, so that can be actually considered to be the influence of the gravity, okay, or the gravitational pull that is kind of acting on the lithosphere, and the buoyancy that I said, because of the resistance that is put up by the mantle of against the pull that is happening on the lithosphere. Okay, so there has to be a balance between these two forces. So isostasy in itself is the the state where the gravitational pull that is exerted on the plate, on the tectonic plate, is balanced by the resistive force that is exerted by the mantle, so that the plate does not sink. So as we had studied in when we were talking about the Earth's interior, that the crust in itself, okay, is less dense when compared to your mantle. So the density difference itself actually helps in the flotation of the lithosphere on the mantle. Okay, since crust is lighter than mantle, it will float on top of the mantle. So that is one of the one of the principles that is already in the play. Now, what happens when it's not always that the thickness of the lithospheric column remains the same, or the density of the column will remain the same. Okay, so if erosion is happening, your lithosphere is getting eroded. Okay, so then the entire length of the lithosphere at or entire thickness of the lithosphere at that area, it is reducing. So when it is reducing, there needs to be kind of adjustment below. Okay, so that this reduction in the thickness is it does not allow for the lithosphere to bound back totally. Okay, so there has to be adjustment, and that adjustment again is done by the mantle by mantle itself. Okay, where it adjusts the force that is the resisting force that we were talking about, so that the lithosphere kind of keeps floating and also does not totally rebound back. So that balance has to be kept. So to understand, or to kind of see how the this isostasy varies from one situation to another, and how does it actually help in understanding the plate tectonic movements that we see. So there are two models that had been put forth. So one is your Aries model of local isostasy, and Prax's model for local isostasy. So in Aries model, there were some assumptions that were made. Okay, so the assumptions that were made was that the blocks, okay, so each of these are actually lithospheric blocks. Okay, all these columns that we see are different kind of different lithospheric blocks or land masses. Now what Aries hypothesis said, that each of these blocks have equal density but different thickness. Okay, so they all, there is one sea level that is seen. Okay, all of them vary in their thickness, but they have equal density. So if we suppose take the average crustal density for all of these lithospheric columns, so what you can see is that the height is actually adjusted based on that. So more the amount, if you have uh, if this is your sea level, okay, this is your sea level. So if this lithospheric column has more material, above the sea level, and this lithospheric column has lesser material above the sea level. Okay, so the there is a kind of a balanced amount of material. Okay, equivalent amount of material is actually below the sea level. Okay, all the way up to the mantle. These are actually called the lithospheric roots. Okay, lithospheric roots. So you can see that to balance out this excess material over here, the lithospheric root has to be deeper compared to this lithospheric block. Okay, so that is what we are seeing over here. So this, okay, so this has this much extra material compared to this lithospheric block. Okay, so you can see equivalently the lithospheric root of this column is actually more deeper, goes deeper compared to this lithospheric. So this actually place is called the compensation depth. Okay, so the compensation depth is where your deepest lithospheric root is actually found. Okay, where the excess material above the sea level compared to the other lithospheric walls is actually compensated. The weight of that material is compensated at that depth by the extending lithospheric root. Okay, so with Airy's hypothesis, okay, so this is where your compensation depth would be found. But for Pratt's hypothesis, okay, so all the lithospheric columns, okay, have different densities as well as different heights, okay, but their compensation depth actually remains the same. Okay, so if your compensation depth has to remain the same and every block has different density, so different so the material has to acquire different heights above the sea level. Okay. So these are the two different isostasy models or hypotheses that actually help us or that were given actually to understand how changes in density or changes in the thickness of the material of the earth's crust or the lithosphere actually helps in keeping that balance where the lithosphere can float on the asthenosphere. Now, one example of isostasy, easy example is that, so when the mountain is building, okay, so we had seen over here to compensate this extra material over here, the root has to go deeper. Now, if the root is has to extend deeper, that means more and more material is actually moving down. Okay, so the compensation depth will also have to move down. Okay, so that is what we are seeing here. So the mountain is building. Okay, so if more material comes up over here, this lithospheric root has to move downwards, okay, into the mantle, and for that the mantle has to kind of flow away from this point to increase the compensation depth. So this is how that isostatic balance is maintained. Now, if this entire amount is eroded away, as we see over here, the mountain is eroded. Okay. So, now this thickness actually decreases. Okay, the thickness decreases, and the lithosphere, due because it is denser, because it is lighter than the mantle, it will rise on top. Okay, so the weight is being removed, so it will slowly rise on top, and when it rises on top, the mantle actually kind of flows back to the space that has where the root has been now gone above, okay, to maintain the balance. So this is also called crustal rebound. Okay, this is an example that we see in where you have very thick glacier. Okay, this is actually happening in areas where there were thick glacier coverage uh, previously. Okay, now since the glaciers are actually melting away, so the crust over there is actually rebounding. Okay, so the mantle, so the depth to the mantle is actually decreasing in those areas. So this is where understanding the isostatic balance is important. If the the depth to mantle actually if it gets more shallower, that means more kind of heat is also coming closer to the earth's surface. This is also one of the kind of applications or one of the examples of how isostatic balance changes with time. So all in all, these actually help us in understanding the plate tectonics. Plates are moving on the mantle, as we said. Okay, so due to these due to the movements of the plates, we have different kind of processes happening all across the world. Now, previously there were two models which were given. So we actually have the plate model as the one that we uh, generally or that we vastly use to understand tectonics, and the plume model is not very widely accepted. So usually plate model is where the plates are moving away from each other as they are floating, and in the plume model it suggests that it's the plume that actually drives the plates, the plate movements. But mostly we say the plate model where the plates are moving, and due to either destruction of the plate or regeneration of the material at plate boundaries, that is the reason why we have the different kind of continental setups. So this is the the important part, that how do they actually what actually drives the plates to move. We know that the plates are floating on asthenosphere, but they could just float. What is causing the movement? Okay, so for that what was proposed was whole mantle convection. Okay, so mantle convection currents are actually the driving force of the movement of the crustal plates, and these are actually because the differences in the states and the temperature of the the layers. So your hot rocks are going to be less dense, okay, and colder rocks are going to be denser. So we know this very common physical phenomena, that hotter things are less dense and then they float on top, and colder things are denser, liquids for that matter, and they they sink down. So the similar rule applies over here. So when a rock is melting, okay, so when a rock is melting, or the rock or the material that is there is hotter, it will rise upwards, okay, and wherever the rocks are say cooling, or the material over there is cooler compared to the adjacent material, the cooler material is going to sink down. So this kind of upwelling material and downgoing material, the movement over here, this in itself is actually causing this whole mantle convection. So what actually is happening is that as the cooler material is going down, okay, suppose this material is going down, as we go down your temperature is going to increase, okay. So when the temperature increases, that means this material is actually reaching a hotter stage, okay. Now over here it has uh, it has become much hotter compared to the material over here, okay. So this was a cooler material, now this has become hotter. Now again, since it is less in density, it will try to rise up. So when it is rising, now this material is hotter compared to this material, so it will rise up. But when it is rising upwards, okay, since again the depth is decreasing over here, so your temperature is going to decrease, and this material again as it tries as it starts to reach the earth's surface, it gets cooler, and because it's getting cooler, then again it will start descending down. So this is the entire kind of the phenomena that actually is driving these convection currents. So these are all different kind of convection cells that are actually created within the mantle because of this hot material rising and cool material going down. So that is why for the convection cells or the convection currents to perpetually keep maintaining these this flow, the transport of heat is important, okay. So where is the heat coming from for the the material to actually become hot or melt and then rise up again, then again cool at around the surface and then descend back. So there are three ways. So one is the internal heating due to the decay of radioactive elements, okay. So uh, the mantle in itself, Earth's mantle consists of a lot of radioactive material or radioactive elements, and decay of these radioactive elements to their radioactive isotopes actually generates heat, okay. So this is one important source of internal heat that actually gives rise to these convection currents. Then you have long term secular cooling of the earth, okay. So earth in itself is actually cooling, as as we said that 4.54 billion years ago it was in a molten state, okay, and it started cooling. So earth in itself is also cooling, the earth's interior has a cooling procedure that is happening, and also the heat from the core, as we had discussed, the inner core in itself is actually solidifying, and because it is it is cooling and it is solidifying, there is heat generated even there, and that itself again is transported through the core to the mantle, and it again helps in keeping this mantle convection in place. So based on these rising material and descending material, so the plate tectonics were based on these. And because in places where suppose you have material coming up, so this is your earth surface, okay, and this is your kind of convection cell that is created, okay. So if this is your convection cell, okay, so material that is coming to the surface over here is actually going to drive the plate away from each other, okay. So you can see in this area over here the material is actually coming on top. This is where the upwelling is happening, or the hot material is coming on top. So what is happening is this area, these two adjacent plates are actually moving away. Now similarly, as this is moving away, the material is being transported over here, okay, okay, and it is maintaining this, okay. So there is no the plates are moving away. Now over here where the plates are coming close to each other, okay, there is collision, and when the collision is happening, some material actually goes down. So when this material is going down, it will again start heating, okay, and then it will get passed on to this because of the convection current that is there, okay. So this is the entire process of how the convection currents are actually giving rise to the plate movements over here, as I said, okay. So the hot material is going to come to the surface, okay, then it is going to cause these plates to move away from each other, okay. Now this material is this plate is moving from here, okay, then it collides with this plate, okay. When the collision happens, because because the apparent difference in the densities, okay, so this is actually cooler material, okay. So cooler material is coming in contact with hotter material, and since the density of the cooler material is actually higher, it will start descending down. Over here it will melt again, and then again it will give rise to such convection current. Some part of it will go on this side and some part of it will go in this convection current, okay. So based on these different mechanisms, we have three important plate boundaries. We have divergent, convergent and transform. Okay, so divergent is where the plates are moving away from each other and material is coming up from the mantle to the surface. Convergent is where the plates are coming towards each other, okay, and some part of one of the plate, actually some part of that plate actually goes below the other plate and it starts descending down into the mantle, okay. So the material is going down into the mantle at the convergent plate boundary. In transform plate boundary, there is no creation, or there is no per se material coming on top, or some material going down, or even if that is happening, the magnitude is very low compared to what it would be in the divergent and convergent plate boundaries. Now in transform plate boundaries, mostly what happens is that the plates are actually moving past each other, okay. So one of them is going to move in this direction and the other is moving in this direction, okay. This can happen suppose where the convection currents below the two plates are actually in the opposite direction to each other. So they will move just past each other, they will not have probably any separation or divergence happening between them, okay. So these are the three major kind of plate boundaries that we see when we are talking about plate tectonics, okay. So sometimes these can be represented on maps or different diagrams that we see in in this form, where this actually shows some space between the two plates and the two plates are moving away from each other. So you draw two parallel lines, and over here if you see that one of them is actually this is the convergent boundary. Okay. So, this triangles that we see over here are actually because this plate is moving on top of this plate. Okay. So, if this is your plate A and this is your plate B, this plate A is actually going on top of the plate B. This is called the overriding plate. Okay. So, the material from overriding plate is not going to descend down. This plate, this is called the subducting plate. The material from the subducting plate actually goes down to the mantle. Okay. Then again it sets up the convection current. And then the last one over here is the transform fault, where the arrows actually show in which direction the plates are moving against each other. So, over here the arrows are showing how the plates are moving towards each other, and over here you can see that the arrows are pointing where the plates are moving away from each other. So, these are where single examples of where single type of boundary is present. Now, so there are cases where there is a combination of different kind of boundaries that are present. Now, over here this is actually your divergent boundary, this is also your divergent boundary, and between these two this divergent boundaries you can see there is a transform boundary. So, over here you can see that because of the movement of the plates, different kind of boundaries are actually forming like in combination with each other. Over here because of this is your overriding plate. Okay, so this is moving towards this side and this is subducting. This plate is subducting. Okay, and because of this movement there is another transform boundary that is created with this plate. Okay. So, over here you can see that maybe the convection current direction is in this direction and the convection current over here is in this direction. So, this can also happen. Over here similarly you can see how this is similar to the this B example, and then over here you can see that there are convergent boundaries, and between the convergent boundary there is a transform boundary. Okay, so there are different kind of scenarios where you will find different boundaries actually uh, uh, happening or forming close to each other. Okay. Now, there is a important kind of plate tectonic setting that we see is where a triple junction is formed. A triple junction is where three plates actually meet at one point in itself. Okay. So, there are two types of triple junctions, you have stable and unstable. Stable is where the relative motions of the three plates are actually not going to change the kind of setup that is there, only then it is called stable. So, that means that if there is a convergent boundary, okay, it will remain a convergent boundary with time. Okay, even after time passes, if all three boundaries have a certain kind of orientation or the process that is happening, that is going to stay, it is not going to change, or not that one plate is totally consumed because there is only subduction happening on one side. Okay. So, at such areas you will have stable. Now, unstable is where for a moment there is kind of one geometry that is present, but as the plate tectonic processes are actually they continue, these this kind of geometry that was present actually changes. Okay. So, then it becomes an unstable. So, there are some places where four or more plates actually meet at one point. Okay. And that will always be unstable. And because there are the number of plates have increased, sometimes what happens is there are multiple triple joints also that are forming. Now, this figure over here actually shows the different kind of geometries that can occur, okay, and the stability that is there. So, one of the most stable triple junction is actually RRR. RRR is that all three plate boundaries are actually your divergent plate boundaries. Okay. So, all the plates are moving away from each other, and because they are constantly moving away from each other, that setup or that geometry is not going to change. Okay, it is going to remain in that manner. Okay, all the other ones that you see, that after a certain time, they, if they are stable in the start, they can, you know, become unstable after a time, or if they are unstable in the start, because of the changes in the geometry, it could become stable for a while. Okay, while this transform fault, okay, so all the three plate boundaries are actually transform fault, transform fault boundaries. So this is going to be unstable, because they are constantly, you know, moving past each other. Okay, so this actually, you know, later on this plate is going to be moved away, so this part is not is actually going to become kind of a rift. Okay, if the motion of this plate is, you know, or the velocity of the movement of that plate is actually higher, so you can see that it is unstable, it will change its geometry over time. Okay, so these are the possible geometries that can be found for different kind of triple junctions. Okay, now this is an example of a stable triple junction. Okay, so this is actually the stable one. Okay, where you have divergent plate boundaries. All these plates are actually moving away from each other, and this geometry is going to stay the same even after many years. Okay, now this is an example of an unstable triple junction. Okay, where you have two divergent plates. Okay, and then there is one two divergent plate boundaries and one convergent plate boundary. Okay, you can see this is actually the overriding plate, and this is your subducting plate. You can see because of the kind of movement that is there. Okay, suppose this plate is only present till here. Okay, what will happen with time is, over here this plate is over here this plate is getting consumed. Okay, because this is actually the subducting slab and this is the overriding one. Okay, so over here this is going to get consumed over here, but over here you can see that the direction is changing. Okay, so what can happen is that there, you know, can occur a rift over here. Okay, so these two plates might separate, because you can see that the direction and the rate at which, you know, they are kind of moving. Over here it is subducting. Okay, and this is overriding. So over here this plate will start getting consumed. Okay, so what can happen is a rupture can form here and the geometry will change. So this is what is, you know, kind of, you know, how unstable triple junctions actually keep changing the way the plates are actually moving with respect to each other. So now we know that how plate tectonics happen, what is the mechanism behind this plate tectonics, and the different kind of, boundaries that are present, for each of the plates. So most important features that are actually, found, some of them are oceanic trenches, then you have volcanoes, and then you have hotspot volcanoes also occurring in places. Okay, so these are obviously even mountains, where you have mountain building, those are also, you know, created by plate tectonics. So these are important for us to know and understand what is causing, or, you know, in which situation which feature would be created. So when we come to convergent plate boundary, okay, so the convergence between the two plates can happen when both the plates are oceanic. Okay, so this one, or one is oceanic and one is continental. Okay, and you can have between continental and continental. Now all three of them actually, you know, might create different kind of features. When it is between continental and continental, actually the mountain ranges are formed, because, you know, both of them are actually somewhat similar in density. Okay, so none of them will actually kind of, you know, subduct below the other. Some material will go, okay, but most of the continental crustal part is not going to, you know, subduct below the other one, and due to that actually the continental material is actually going to, you know, rise upwards, and it will create the mountains. Okay, so this is what happens when you have continental to continental collision. Okay, When you have oceanic, okay, again a similar way that can happen is, you know, trenches do form. Okay, when there is a collision between oceanic plate and oceanic plate, one of the most important feature that is, you know, formed is a trench. Okay, it may be a very deep trench, okay, or it may be a shallow trench. It depends on the kind of, you know, material over there, or the you know, velocity with which each of the plates are moving. When it is between oceanic and continental, it is essential that the oceanic plate actually subducts below the continental. Why? Because continental crust is lighter compared to your oceanic crust. We had seen this when we were discussing about the Earth's crust. Okay. So, the oceanic crust will subduct below the continental crust, okay, and over there again you will form a trench. Okay. So, this is how the you know, different setups or scenarios can be found when we are talking about convergent plate boundaries. So, over here, you know, this is kind of like a cross section, you know, if you take through the, you know, perpendicular to the kind of collision that is happening, or the subduction that is happening. So, over here you can see that different kind of geological features that are formed. Okay. So, over here this is the locked zone, where your, you know, the two plates are actually locked with each other. Now, because of the density differences, some part of this plate is actually, you know, going to go into the mantle. It is going to melt, and because of the melting procedure, some part of this melted you know, plate part is actually going to rise up over here and form a volcanic arc. Okay, so volcanic arcs can form when, you know, you have collision between your continental and oceanic crust. So, one very important, or you know, significant feature that has been formed due to the collision between two continents is Himalaya. So, it was between the Indian landmass and the Eurasian landmass. So, because of this collision, okay, most of the you know, kind of features that are formed actually are faults. These are called thrust faults. Okay, so the thrust fault is when two you know, blocks are actually moving towards each other. One of them is going to, you know, move upwards, and one of them is going to move downwards. Okay. So, this fault plane is actually called a thrust fault plane. Okay, and this fault is actually is called a thrust fault. We will I think there are some you know, lectures later on which explain the different kind of faults that we have. So, you can see that before the collision that had happened, okay, so this oceanic crust over here, that is actually belonging to the Tethys Ocean. Okay, we had discussed that there was Tethys Ocean present between Indian landmass and the Eurasian landmass. So, this oceanic crust is actually the Tethys oceanic crust. So, before the collision, you know, when the collision started, you can see that, you know, there are discontinuities that are forming. Okay, there are um, fractures that had formed, that, you know, together they started forming bigger faults, longer faults, and then you know, these actually joined together, and they rose in height also because the collision kept on happening. So, the reference point that was over here, okay, that actually rose up to a certain height, considering the MSL, or the main sea level. So, this is the, you know, how continental convergent boundaries actually give rise to mountain building processes. Now, oceanic trench, we you know, mostly the most famous one that we know is the Mariana Trench. Over here, some part of the Indo-Australian plate is actually you know, is actually converging with the Pacific plate. Now, the Pacific plate, okay, is actually the subducting plate, and because of this because of this subduction process that is happening, your trenches are created over here. Okay, so this part actually it can this is a block diagram, so it's shown. So what happens is like this part and then this part. Okay, so this subducting plate actually drags this material, this overriding plate material also downwards. Okay, so this can go much deeper, where it actually connects and where the subduction starts happening, that could be at a much deeper level, and that gives us the deep trenches, oceanic trenches that we see. And this ring of fire, okay, you must have heard about this, the ring of fire. This is actually all the sections or all the locations where you have trench formation between your Pacific plate and all the different plates that are present. The Indo-Australian plate is over here, and Challenger Deep is one more important or pretty famous trench. And then you can see all the different trenches that are there. Okay, so Challenger Deep, Mariana Trench is over here. All due to the fact that the Pacific plate is converging with either oceanic plates or the continental plates, and they are forming the trenches. Now the next one is the divergent plate boundary. So divergent plate boundary, where the plates are moving away from each other, so new material or new land mass is actually forming in these areas. So these are also called constructive plate boundaries, whereas convergent plate boundaries can also be called as destructive plate boundaries, because over there the material is getting destroyed. Only in continental we see mountain building, but even then we see that a lot of land mass is actually destroyed in that. So two important features that are actually created at divergent plate boundaries is the continental rift and the mid-oceanic ridge. So continental rift is when the diverging is happening between two plate boundaries, continental plates. Okay, and mid-oceanic ridges, when the oceanic plates are moving away from each other, and mid-oceanic ridge is found over there. So the very one of the famous rift systems is the East African rift system. You can see over here. So these are actually continental plates only, and since they are moving away from each other, more and more material is rising on top, and it is forming new land mass over here. Okay, so and this is also called the rift valley. So this is when we talked about the mountain building processes, there we talked about thrust faults. When this continental rift is happening, actually normal faults are the faults that are created. So in the normal faults is, again one is one block of mass is moving upwards and one block of mass is actually moving downwards, but the fault plane is this is actually, I'll have to explain the entire fault system over here, but you can see that over there compression was the mechanism that was forming the thrust, but for rift formation or the normal fault formation, the mechanism is actually where the forces are going away from each other. Okay, so extensional processes play a role when we are talking about divergent plate boundaries, and that creates normal faults, and normal faults help in creation of rift valleys and rift systems around the earth. Okay, so rift systems, when we are talking about any rift valley, any rift system that is created would be created due to divergent plate boundaries. Now mid-Atlantic oceanic ridge, most of us have learnt about it. So this is the example when the oceanic plates are moving away from each other, and the mantle material actually comes up to the surface, and it forms small mountain chains, small or it could be very high also. The heights of these mid Atlantic oceanic ridges or oceanic ridges can be pretty high in some areas where the depth of the oceans are, much, higher. So, the Iceland on a whole is actually situated on top of this mid Atlantic oceanic ridge, and Iceland itself is, kind of breaking apart due to this divergent, plate boundary movement. So, over here you can see that this entire stretch of feature is actually the mid Atlantic oceanic ridge, and Iceland falls right on top of it. So, the last one that is the transform plate boundary. So, the plates are moving away from each other. Okay, so mostly what happens is the material is kind of pulled away from each other, and that causes shearing. So, shearing is the process when we were talking about thrust fault or the normal fault. So, for transform plate boundary, the kind of disturbance that happens between the rocks is the shearing of the rocks. So, because of these movement, okay, so uh, we have the San Andreas fault. Okay, there have been movies also, and we know constantly a lot of earthquakes happen in this region. So, it is because of these the existence of the transform plate boundary in the San Andreas region. So, over here you can see that the western part is moving towards north, and the eastern part, or the North American plate is actually moving towards the south. And because of this, this is one major fault. Okay, so the major fault is forming here, and these are kind of secondary faults that are created because of the uh, movement that is happening against each other. So, the material are actually crushing, and they are moving against each other, so they are shearing. So, these are all shear zones, you can call them as shear zones, and this is the main San Andreas fault that we see. And over here you can again see that even between North American plate and South American plate, there are smaller transform plate boundaries that are present. So, Caribbean plate and American plate, okay, so there is transform boundary between them, as well as Caribbean plate and South American plate. So, these are all due to the different directions in which the plates are actually moving. So, these might be actually subducting somewhere else. Okay, maybe towards the eastern side it might be subducting somewhere else. So, because of that movement, it actually creates a transform fault or transform plate boundary with a different plate. So, this is a better kind of structural diagram of how the plates are there, and how the fault is actually moving, or the plate boundaries, the plates, the movement of the plate. You can see over here that this area is actually a transform, but over here, okay, as we go in the different plates that we see, you can see that this is a divergent plate boundary, then this is again transform plate boundary, and there is a subduction zone that is present here. So, this way you can see that all different kinds of plate boundaries actually can exist in in a in an aerial extent, and they can have different combinations, and because of the relative movement to each other, a different kind of different kind of tectonic setup is actually created because of that. So, similarly for in the Indian context, okay, so the most important plate boundary feature that we have is the Himalayas. Okay, and the another important plate boundary movement, or plate movement feature is the formation of the Deccan basalts. So, Deccan basalts was formed due to the hotspot or movement of the Indian landmass over a hotspot, a plume hotspot. Actually, we are a little low on time right now. We are already reaching 8. So, I can continue some part of this in the next lecture, or you can go through the these slides, and if you have any questions, you can put it in the uh, discussion forum. Otherwise, I will actually spend a few more minutes in the next class to kind of just go through how the different kind of plate boundaries and the plate movements actually affect the or cause natural disasters, as we will see in the Sumatra Andaman tsunami case, as well as the recent last year earthquakes in Turkey. So these two are good examples to understand how the different plate movements, or the strain or the stress that is released due to the such plate movements actually cause huge uh, disasters. So I will stop here now, since we are already it's already 8. So thank you for joining, and as usual the NPTEL team will update the recorded video and the content as and when they they have it scheduled. So if you have any quick question, maybe we can discuss. So if there are no questions, then hopefully if you have any doubts or any question other than the content that is here, to understand something more, you can put it in the discussion forum and I will try to answer them. So thank you for attending. Hope to see you in the next weekly session.
Thank you, ma'am.